I'm told the website is down, and I apologize. I posted something there this morning, so something must have screwed up when I did that. So I apologize for that. I'm also apologizing in that I'm really having a hard time staying ahead of you guys in terms of getting keynotes and PowerPoints together. You're probably seeing that yourself. So I'm working to get faster on top of that, but it is a challenge doing that for the first time from the new book. But I will see what I can do to get things through and out faster so that you can get them uploaded. But anyway, the website appears to be down, and I'll fix it after class. So I apologize if you don't have the PowerPoints in front of you today. We are turning the corner now. I said we are almost through talking about enzymes in general. And today's lecture actually is about a group of enzymes that we'll talk about specifically that are pretty critical. Without blood clotting, we're not here. People long ago who had hemophilia didn't live very long. I've got a statistic later in today's lecture where I think the average age used to be about 11 or 12. Today it's about 60, thanks to advances in molecular knowledge. We think about the process of blood clotting. Blood clotting is a remarkable thing. We can cut ourselves and go from a state where we have no blood clotting going on to forming a clot in a matter of minutes. And in that matter of minutes, that clot that forms from proteins that are floating around the bloodstream that aren't forming the clot in the absence of the injury. And they're forming a watertight seal in minutes. And they're forming it from proteins. It's absolutely remarkable. We don't want those clots forming in the absence of injury because that's known as causing a stroke or causing a heart attack when those clots occur in the wrong places. If you have phlebitis, which some people do, which is a painful disorder in your legs, that it's most commonly found in the legs, that arises from clotting that happens in arteries or in the blood flow of your legs. Very, very difficult. But for the most part, our blood clotting system works really, really well. And not only does it work really, really well, it works really, really fast. So we're going to see some cool things that cells do to make that happen today. We're going to talk about serine proteases because there's a whole group of serine proteases that are involved in what I call the clotting cascade process. And I will I'll be honest with you that today's lecture is a challenge for me to give. And it's a challenge because I'm giving the blood clotting lecture in a little different way than I've done in the past. And I've tried, maybe not successfully, but I've tried to keep as much detail out as I can without letting you lose the picture. So you're going to see there's a fair amount of detail in today's lecture. It's a challenging lecture to give because there's a lot of factors and a lot of proteins. I will try to focus you on proteins and factors that I think that you should focus on and try to keep you from getting lost in the forest. I don't want you looking at too many trees. I want you to see the bigger picture of the forest. And that's really what we're after here. Most of what I will focus your attention on will be the end of the process, where the cells are actually forming the clot. Okay? So with that big introduction, let's turn our attention to the blood clotting process. Now, on the screen, and by the way, you're going to see in the beginning of the lecture, I'm going to give 2 or 3 different figures showing a lot of complexity to the process. You're not going to draw these figures. All right? So I'm not going to ask you on an exam, regurgitate this figure. That's not what the point is here. I will go through and try to give you big picture things, and I want you to try to understand things as big pictures and not as details. So you don't need to know, for example, that factor TF7A converts factor 9 into an active form. All right? I may talk about that, but I'm not going to ask you questions at that detail on the exam. Well, as we look at the clotting process, this is one view, and as I said, I'm going to show you 3 views of the clotting process. I like to start with this one because this figure shows us that the clotting process has 2 big features. One feature is called the cellular response, and it's actually the first response that happens when an injury occurs. Okay? The very first thing that happens when you cut yourself or you hurt yourself in some way is the cellular response. And the cellular response manifests itself through blood platelets. Now, the blood platelets do a variety of things, but one of the most important things that they do is that they start plugging that hole. They don't completely plug it, but they start the plugging process. And in doing so, they start the other process going, which is the molecular response. The molecular response you see on the screen is a much bigger response, and it's ultimately what forms the clot. Now, it's in that molecular response that a lot of detail comes up. Okay? A lot of details popping up in that molecular response. I want you to focus your attention down on the end of the process. Focus of activity. Oh, except the Y got cut off, doesn't it? All right. I want you to focus your attention on the bottom of that, because fibrin is a molecule, it's a protein molecule, that forms polymers, and those polymers form the clot. So when you see a blood clot that is, a clot that is on your skin or something, that's a polymer of fibrin. Now, I'm not going to talk about the details. Fibrin actually has 2 different subunits that form the polymer. I'm not going to go through that detail with you. But you should know that fibrin is made, the fibrin units go together to make a polymer. You also see on that screen that fibrin comes from a zymogen known as fibrinogen, and that's to the right on the screen. And you can see that fibrinogen is converted into fibrin by this protein known as thrombin. And you can see that thrombin has a zymogen form known as prothrombin. Now, I'm repeating those because those are the central parts of the clotting process that we'll focus on. Okay? So we've got 2 zymogens there that are very important, prothrombin and fibrinogen. There's a third, and I'll call it a different name later. You see it on that bottom screen. It says XIIIA. That stands for 13A. And throughout these figures that I'll be showing you, wherever you see the subscript A, that means active. So, for example, factor 13 is converted into an active form by action of thrombin, just like fibrinogen is converted into fibrin by action of thrombin. Thrombin is a serine protease. All of the proteases involved in the blood clotting scheme that we'll talk about are serine proteases. Okay? All of those are serine proteases. So you've learned something about serine proteases already. And we saw how we had a cascading system last time for the proteases, and how I told you that with a cascading system, each level gives a greater increase in the amount of enzyme active. This gets amplified millions of times. The signal in a clotting system gets amplified millions of times by a cascading system, and the cascading system is what you see on the screen. Now, this cascading system is complicated. So as I say, we're going to work on this at a hopefully a reasonable level. Okay, so the cellular response starts, and that's where we're going to start the process. The cellular response starts as a result of damaged epithelial tissue. Epithelial tissue is found in a variety of places in our bodies, but the most important one for this process is it lines the blood vessels. Epithelial tissue lines the blood vessels. As long as the epithelial tissue remains intact, the clotting system sees nothing or no reason to clot, hopefully, right? And when the epithelial tissue gets damaged, as what happens when you cut yourself or you bang yourself in some way, that damages the epithelial tissue, and it exposes the next layer, which is collagen. Collagen, of course, being connective tissue. And it's the exposure of collagen that tells the body we need to start the clotting process. Okay? So there's the very first signal that says it's time to start the clotting. All right. Now, several things happen as collagen gets exposed. Platelets bind to the collagen using collagen-binding surface receptors that they have. And platelets, as I said, are these blood cells that are going to try to form a plug of some sort to start the process. There are proteins in the platelets called integrins, and they bind to the extracellular matrix. The extracellular matrix is the parts of proteins that are found outside of cells that help hold things together. That's where the collagen is found. And they're anchoring those platelets to the site of the wound. This protein called the von Willebrand factor, okay, is a very important protein in the overall process, and we'll see it actually coming up later in the molecular response as well. The von Willebrand factor does a variety of things, all right? But one of the things it does in the cellular response is to form additional links between the platelets' glycoprotein, glycoproteins are on the surface of the platelet cells, and the parts of the collagen. So they're helping to stick the platelets at the place where the wound has occurred. Okay. There's an amplification process. And amplification is, of course, what we want to have because we want to take a small signal and make many more, a big signal out of it, right? If we see an accident on the road and it's night time, we want to not have a candle that we hold up to let other cars know that there's an accident. We want to have some big, bright, flashing light. So that's the amplifying that's happening. And the amplification process does two things in the cellular response. Okay? It releases a platelet factor, and no, I don't care if you know the name of it, that inhibits heparin. Okay? Heparin is an anti-clotting factor. So by inhibiting the anti-clotting factor, you are favoring clotting. Okay? The second thing that happens is that the platelets release, that the tissues release thromboxane A2. And what this does is it causes the platelets to get very sticky. If you're going to form a plug, you don't want everything flying apart. You want it to be sticky, and that's what's happening here. Okay? Calcium is released from the intracellular stores of cells in the area. Okay? And that GQ cascade is just a name for the way in which this happens. I don't care that you know the name of the GQ cascade. But the release of calcium is very important because that will play a role in the molecular response. Okay? And as I said earlier, wherever we had the subscript A, that means it's the activated form. Okay, so this summarizes in 6 steps the cellular response. The cellular response is a prelude to the molecular response, and the cellular response is telling the molecular response, hey, we got to do something here. I'm not going to ask you to draw that on the exam either. I couldn't draw that on the exam. Okay? There's a lot of information there. All right? Look at all the factors. And it's drawn in a way that was different from before. And what you're going to see as I go through the lecture is that these factors, we don't have A goes to B, goes to C, goes to D in blood clotting. We have A going to B and G and inhibiting H, right? And that's part of what this is trying to depict on the screen. There are things that favor clotting, things that favor breakdown of clots, and some of them actually work in the same pathway, which is kind of interesting. But this thing has to be orchestrated very carefully because we don't want clots forming where there shouldn't be a clot, and we want clots to form as quickly as possible in places where we need a clot. This figure I like to show because it depicts 2 parts of the molecular response. The first part being the what's called the contact activation or the intrinsic pathway. The second part being the tissue factor pathway or what's called the extrinsic pathway. These are separate pathways, and they have separate stimuli, which I won't really talk about. They both involve trauma. Okay? But the important point about these pathways isn't the individual steps in the extrinsic or the intrinsic pathways, but rather the fact that they converge to stimulate the things I told you about earlier. The conversion of prothrombin to make thrombin, the conversion of fibrinogen to make fibrin, and the activation of this factor 13A. Okay? Okay. This cleans up that last figure quite a bit. All right? We can see the intrinsic pathway shown in, I guess is bluish on the left. The colors don't come out very well here. Okay? And we can see that there's a series of factors that get activated. Every place on that screen where you see an arrow pointing downwards, that's a serine protease activating the next thing in the system. Every single one of those is a serine protease that's activating the next one in the system. So if I have 1,000 factor 12s, or 12As that are, of course, the active form, that are converting factor 11 into 11A, 1,000 of the 12As might make 1,000,000 of the 11As. The 11As can convert factor 9 into factor 9A. That might make 10 million. So we see a growth in numbers at every step of this process. We see the amplification going on. And what's interesting, we'll actually see a different kind of amplification that will occur as we get down to that boundary between the blue and the yellow. Okay? So the molecular response happens in two phases. It happens in what we call an initiation phase, and it happens in what we call an amplification phase. They're actually both shown on the screen right now, so I can't say there's one versus the other. They're both shown on the screen right now. Okay? So we see that the extrinsic pathway has really only one reaction that's unique to it. And the extrinsic pathway has a lot of overlap with the intrinsic pathway. That's shown in yellow at the bottom. But we're focusing again on the prothrombin going to thrombin, the thrombin catalyzing the conversion of fibrinogen to fibrin, and the conversion of fibrin into a stable clot. That's actually what factor 13A does, and we'll see that in just a bit. Oh, okay, I should also point out, actually, that's the focus I wanted to say right there. You look at the names of the factors that are above, factor 12, factor 11, factor 9, those are all Roman numerals, of course. And I'm not asking you to memorize those names. Okay? And I just show those on there so that you can see, wow, there's a lot of serine proteases that are involved in this process. Not everything is a serine protease. But every place where you've got an arrow pointing downwards, that's a serine protease that is acting to convert something. Okay. Well, let's look at the molecular response a little bit more closely. I love this electron micrograph, by the way. That is an actual clot, and you can see blood cells embedded in that clot. It gives you an idea about, wow, that is an incredible tangle that is actually there. That tangle is watertight, will not leak water. Of course, you know that with blood clotting. All right, so the molecular response converges on the polymerization of fibrin, which is what I've already told you. And that comes from the action of both the intrinsic and extrinsic pathways that come together to activate as much fibrin as possible, as quickly as possible, but not too much, because too much will be a problem. And that's probably why there's such complexity in these pathways, because it allows for fine-tuning in terms of amount of clotting that's actually needed. Okay? The intrinsic pathway is known as the contact activation pathway, and the extrinsic pathway is known as the tissue factor pathway, and that's what I told you. The extrinsic pathway of the two is the more important. Okay. All right. So let's take a look at the initiation phase of the molecular response. And I've tried to depict part of it right there on the screen for you. And I will tell you that you're going to see all these different figures I'm going to show you. As I say, I'm not going to ask you to redraw these figures. If you focus your attention on the text that I've written about them, you'll be in best shape. And I'll also summarize these in the highlights. Okay. So, in the initiation phase of the molecular response, the tissue damage that happened in that cellular response stimulates the formation of a complex. All right? That complex has a name, TF, factor 7A, for what it's worth. Okay? This complex with some other things activate factor 10. And notice, since I didn't name those other things, if I don't name them, then you're not responsible for knowing them, right? Nobody's smiling. That's not funny, Ahern. There's too much information here, right? Okay, so we are activating factor 10. You can see factor 10 on the scheme, about in the middle of the figure below, where factor 10 is going to factor 10A. And we can see that factor 10A is important because factor 10A, that being the active form of factor 10, is what converts prothrombin to thrombin. You might say, oh, we're done then. We've converted prothrombin to thrombin. Thrombin can then activate the clot, etc., and we're not, unfortunately. Okay? It'd be nice if we were. This is not responding. Oh, come on, you. Okay. Now, after the initiation phase happens, an amplification phase happens. Now, why does that happen? The reason that it happens, and I think I'm jumped. Did I jump? Yes, I did. Okay. I thought I did. All right. Okay, that's what I'm after right there. All right. So the point number 3 is a very important one. Okay. These factors that have been activated here, factor 10 being the most important one there, but these other ones that I'm not going to name there, these guys inefficiently convert prothrombin into a tiny amount of thrombin. You begin to see why this is the initiation phase, because only the result of this action that I've described to you, only as a result of this action do we see any thrombin being activated. Now, thrombin, as we will see, plays a role in amplifying a process that amplifies itself. It's a cyclic process. If thrombin activates something, that activates something, that activates thrombin, you can see every time you turn the cycle that you're going to get more and more thrombin, which is going to activate more and more thrombin, and it gets bigger and bigger and bigger. And that's what happens in the amplification phase. So the initiation phase, we only get a tiny amount of thrombin active, but that's important. One thing I didn't point out here is that you notice the involvement in steps 2 and 3 of calcium. I told you at the end of the cellular response that the release of calcium was necessary for the next phase, and this calcium here is very important. We'll see calcium playing a role later in the lecture as well. Okay. All right. Now, the thrombin, therefore, is the key to the overall process that's happening right here. We see thrombin is going to play roles in a lot of things, and thrombin is going to be part of our focus, as is prothrombin. Don't confuse prothrombin, which is the inactive form, with thrombin, which is the active form. I'll talk about that later. Okay. So let's now look at the amplification phase that I've been describing to you. So the amplification phase is what's happening in the sort of boundary between the blue and the yellow. It's happening in the boundary between the blue and the yellow. It requires factors from both the intrinsic and the extrinsic responses working together. All right, how do we start? Well, we start the amplification phase with factor 8. Okay? Factor 8, you can see, is on the blue side of the equation. It's up there with PL and calcium. And it's involved in the activation of factor 10. Factor 8 is critical. Okay? Normally, factor 8 is bound in a complex with the von Willebrand factor. Okay? Only after that cellular phase has started to occur does factor 8 get released from the von Willebrand factor and activated. That's also necessary for the amplification. So as a result of the factor 8 being released, amplification now is able to occur. Factor 8 has been released. We see that factor 10 is increased in increasing amounts. Okay? Factor 11, which is way up at the top, helps favor the production of more factor 9. So here's our cascade. I'm sort of going backwards here, aren't I? Factor 11 activates factor 9. Factor 9 is necessary to activate factor 10. And factor 10 plus activated factor 8 stimulate the production of factor 10A. That 10A is very critical, as you've seen, because we need that to make thrombin. And when we made factor 10A previously, we made tiny amounts. That's why there's only a very tiny amount of thrombin that's been made. We've now started to make a lot of factor 10A, the active form of 10 is 10A. And we have increased the amount of factor 10A being made by 3 to 4 orders of magnitude. That means 1,000 to 10,000 fold. So in this amplification phase that I've just described, we've started to make a ton more factor 10A. Factor 5A, which I haven't talked about, and factor 10, along with calcium, make a ton of thrombin. They're converting prothrombin into thrombin. Okay? Oops, I jumped ahead. Okay. Now, thrombin, in turn, I hate this. Thrombin, in turn, can feed back, and we'll see how it activates later, but thrombin, in turn, can go back and stimulate the production of these other factors, that is, the activation of these other factors that in turn activated it. So as I said, we turn a wheel. We've turned a wheel and we've just increased the production of thrombin by 1,000,000-fold, and now the production of more thrombin is going to favor the activation of these other factors that made thrombin, and the wheel turns. Every turn of the wheel making more and more and more thrombin. We're making a tremendous amount of active thrombin. So the amplification phase has occurred at this point. That's the worst of it. It gets better. Okay? Now, so once we make thrombin, we make plenty of fibrinogen because thrombin converts fibrinogen. I'm sorry, we make plenty of fibrin. We convert fibrinogen into fibrin by action of thrombin. If we have a ton of thrombin, we're going to have a ton of fibrin. And fibrin is a self-polymerizing molecule. Self-polymerizing. It's like a jigsaw puzzle putting itself together. We talk about nanomachines and we think what nanomachines can do. A self-polymerizing molecule is a nanomachine. It's assembling itself into a longer and longer polymer. So the action of all this has been focused on making more fibrin, and more fibrin happened because we had more thrombin. The amplification gave us plenty of thrombin. Everybody got me on with that? You guys need a joke. You want a joke? Okay. So this is, have I told you the joke about the crunch bird? The crunch bird? Okay. So this lady goes off, she wants to get her husband this present, right? So she goes to the pet store and she walks in and she says, I want to get something for my husband for his birthday. The pet shop owner says, oh, no problem. He goes out and he grabs this iguana, brings it out on a leash and says, how about this? The lady says, oh, I don't think I want that around the house. Okay. But she says, I want something really unusual. He says, no problem. So he goes back and gets this long anaconda, pulls it out. She says, no, I don't think I want that in the house either. So he tries this with animal after animal after animal, and of course, every one is just not quite right. He's throwing up his hands in the air, and finally he says, I know. He says, you need a crunch bird. And she says, what's a crunch bird? He says, look at this. He points over across the room, all right, and there's this little tiny bird sitting on a perch over there. And he says, crunch bird, chair. And this bird jumps up, flies over, and goes over to this wooden chair and demolishes the chair. Little tiny bird. In front of her eyes. It splinters by the time the bird's done. She says, that's amazing. He says, you ain't seen nothing. Crunch bird, desk. And there's this big wooden desk, and the bird flies over to this desk and just kapow, in literally a minute, this desk doesn't exist anymore. And she says, oh, I got to have that. I got to have that. He'll love this. So she goes home and she walks in the door. She got this little tiny bird on her finger. She says, honey, I got you something for your birthday. He's looking at the newspaper and he says, what is it? She says, it's a crunch bird. He says, crunch bird my ass. Okay. I love how the titter just kind of goes through the crowd. You can just sort of follow it. It's kind of cool. I wish my lectures got that kind of response, but the jokes do better than the lectures do. Okay, so I've said we're through the worst part. we've made a polymer of fibrin, and that polymer isn't the final clot. Okay? The polymer is not the final clot. All right. Whoop, what happened there? I'm not going to go through that. I thought I did that. Okay, here's where I was. All right, the clot actually requires stabilization. So the polymer forms, but the polymer doesn't hold itself together well. Little pieces stick into each other and so forth. But to hold the polymer together, you need covalent crosslinks. And the covalent crosslinks happen as a result of action of an enzyme known as a transglutaminase. And transglutaminase is factor 13A that we saw before, that thrombin actually activated. Okay? What the enzyme does, what transglutaminase does, it catalyzes the joining of the amine groups, okay, off of glutamine, all right, to the carboxamide, the amine is lost in the process, but the carboxamide of a glutamine to the amine side chain of lysine. That's what's happening in the top reaction. You can see that the ammonia is released, and we form a covalent bond between the first polypeptide chain of fibrin and the second polypeptide chain of fibrin. So the bond between the carboxamide part of glutamine, which is on the left, to the amine of lysine, which is on the right, is a covalent bond. Anytime in space you have a lysine adjacent to a glutamine, this reaction will occur. So we got this, you saw that mess and tangle of a clot that we had in that electron micrograph. You could imagine there's going to be a ton of these individual side chains that may be close to each other, and they're going to be joined in a covalent bond. This is called hardening of the clot, and the hardening of the clot is necessary for the clot to be stable. And if you ever cut yourself and you ever look at a clot closely, you'll see the very first thing that forms is fairly fluid. It's not hard as it gets later. And that hardening is happening as a result of the process you see here. Now, the bottom part of that figure shows you how the process can be reversed. I won't go into that because I'm going to talk about an enzyme that does that later. This schematically shows you what's happening. Okay? All right? This is showing you what's happening with the overall thing. And we have the top or the middle figure there where it says fibrin mesh. That's the polymer that has started to form. And then the factor 13A, the transglutaminase, causes covalent bonds to be formed. They're shown as diagonals in that figure. So all those cross-linked covalent bonds stabilize the clot. Okay. So let me summarize a little bit for you. Prothrombin converts fibrinogen to fibrin. Prothrombin is a serine protease. Okay? Prothrombin must bind calcium to be at the site of the wound. Notice I'm talking about prothrombin. Prothrombin is not an active serine protease. It's a zymogen of a serine protease. But prothrombin must bind calcium. If there's one thing you want to take away from here, that's it right there. Prothrombin must bind calcium. Not thrombin. You want prothrombin to be at the site of the wound because that's where you want the enzyme to be activated. You don't want it to be activated floating out in your bloodstream because then you're going to form clots that you don't want. All right? So what I'm going to show you in a little bit is how vitamin K helps that to occur. There it is right there. Vitamin K, okay, is required by an enzyme that catalyzes the addition of a second carboxyl group to a glutamate side chain. You can see that reaction occurring there. There's glutamate on the left. Glutamate on the right. The normal glutamate is on the right. And it only has one carboxyl side chain. That one carboxyl side chain cannot bind to calcium. In order to bind to calcium, a second carboxyl group has to get put on, and that's what you see on the left. And you can see how calcium fits nicely in that little pocket. And that facilitates the binding of calcium to hold it at the site of the wound for prothrombin. Let's look to see how that process occurs. Okay? Vitamin K is necessary, so if we block vitamin K, we can reduce clotting, and I'll show you that in a second. Okay, at the top you see fibrin. That's the fibrin, part of the fibrin polymer up at the top. Okay? So tissue damage initiates a cellular response that starts the process. We get sticky platelets, releases calcium. Okay? The tissue damage starts the intrinsic and extrinsic pathways, which are the molecular pathways, the molecular response. Okay? The intrinsic pathway and the extrinsic pathways favor the polymerization of fibrin, as we've seen. Okay? The molecular phase the molecular part has an initiation phase that I've described and an amplification phase. The first initiation phase makes only a small amount of thrombin, and the amplification makes a ton of thrombin. And finally, thrombin activates fibrinogen to make fibrin to form the clot. Okay. All right. Now, I said I'm going to talk about vitamin K. I think I've got my slide a little bit out of order there. I apologize for that. But I will come back to that in a second. Diseases relating to blood clotting, you know, hemophilia. So there are two factors that are commonly deficient in people who have hemophilia. Factor VIII, which is the one that the von Willebrand factor holds on to, and is also involved in the amplification process, is deficient in people who have hemophilia A. People who have hemophilia can't properly clot their blood, and they can bleed to death if they don't get these factors. The reason we've improved life expectancy for people who have these diseases is because we've been able to, in the laboratory, make factors necessary that are missing in people who have this genetic disease. The other common deficiency is factor IX, which is also involved in that amplification process. So deficiency of factor IX leads to what's called hemophilia B, and that was the factor that was transmitted through Queen Victoria's family. She had several descendants who had hemophilia. Okay. So as I note, in 1960, the life expectancy of a hemophiliac was 11 years. Today, it is over 60. And the reason it was 11 years was there wasn't a good way to get enough clotting factor. The way that people got it was you can't really get it from people easily. You can't get it in large enough quantities. They would take it out of cow blood, and people who got those would oftentimes develop antibodies against it instead of actually having to help them. So it wasn't a good factor. Today we make it by bacteria. We make it with biotechnology. We make human, so there's no immune response to it. Human clotting factors. Okay, a related disease to hemophilia is von Willebrand's disease. And that comes from deficiency of the von Willebrand factor. It's similar. Okay? This factor is a protein. It's a glycoprotein. Right? And I've already described to you the role that it plays, so I won't go through that. It does help to anchor the platelets. Okay? And it's binding to a platelet glycoprotein. That's what it's doing. Okay? It binds to heparin. Heparin was the anti-clotting factor. So by binding heparin, it's inhibiting the action of heparin, and it's inhibiting the anti-clotting to favor the clotting. Okay? It also binds to collagen. This factor is involved in a lot of things. And most importantly, for that amplification process, it binds to factor VIII in the molecular response. When the von Willebrand factor is bound to factor VIII, the factor VIII is not activatable. So von Willebrand factor is floating around in your bloodstream all the time, holding on to factor VIII unless there's an injury. And only when there's an injury will factor VIII be released from it to be activated and then go play a role in that amplification process. Okay? So von Willebrand factor holds on to it until there is a wound. All right, here's the vitamin K. So I've got to rearrange those slides. But the vitamin K plays a role, as I said, in the carboxylation of glutamate side chains of several proteins. The most visible one for our purposes is prothrombin. We'll see vitamin K occurs in several forms. Here's one form in which it occurs. Okay? It's a fat-soluble vitamin. It's one of the 4 fat-soluble vitamins. A, D, E, and K are all fat-soluble. Okay? Vitamin K also plays a very important role in bone health because it plays roles in calcium metabolism. It's stored in fat tissue. You get it in your diet most abundantly in green leafy vegetables. Okay? Eat lots of green leafy vegetables. It's stable in air. It decomposes in sunlight. Comes in multiple forms that I'll show you in a second. Okay? And the modifications that it plays a role in help all the different proteins it interacts with, or that get this modification to bind calcium. Okay? Absence of vitamin K, uncontrolled bleeding. That makes sense, because if you have no vitamin K, you can't carboxylate prothrombin, and if you can't carboxylate prothrombin, you can't hold on to calcium, and if you can't hold on to calcium with prothrombin, it won't be at the site of the wound. You will bleed to death. Okay? We talk about blood thinners and people who take blood thinners. Anybody who's on a blood thinner, like I'll describe in a minute, has to go to the doctor periodically to get their level of blood thinner measured, because if it's too high, they will hemorrhage and die. Okay? So they're very carefully calculating how much you're inhibiting vitamin K if you're on a blood thinner. Okay? Deficiency, and this is an important point, deficiency of vitamin K is rare in adults. That's why you don't see vitamin K supplements. And you probably wouldn't want to take them anyway, because you don't want to facilitate too much clotting, right? But you should eat your green leafy vegetables. Your body controls. You'll see that your body controls how much vitamin K is actually made. And bacteria do that for you. Okay? All right, so vitamin K is a group of molecules, a bunch of names. All right? No, you're not going to know the structures, and no, you're not going to know the names. But I'm showing them to you so you can see the variety of things that are there. Yes, question? What's that? Mm-hmm. So when infants are born, they're given a vitamin K shot. That's a good question, actually. Vitamin K is mostly obtained in you from action of bacteria in your gut. And I'm not a medical person, but my expectation would be that the bacterial flora in the infant gut, especially if it's a preemie or something, may not have been properly established, and so they want to make sure they have sufficient vitamin K to clot. That, again, I don't get medical advice, but that would be my expectation. That's the case. Okay, so vitamin K is in plants because it's a part of the photosynthetic system. It's an electron acceptor. Okay, they say it's found in the green leafy plants. It's involved in the carboxylation of a bunch of blood clotting factors. Factor 2 is prothrombin. Okay, factor 2 as another name for prothrombin, but you can see other ones that are affected. It's also involved in carboxylation of anti-clotting factors. So we can see it's playing both sides of the system. Okay. And you can see a variety of structures. Here's yet another one. There are 4 primary forms of vitamin K, and as I say, I don't even care that you know the names of them. Okay. Now, the actual carboxylation is shown on the screen. The actual carboxylation the vitamin K plays a role in is shown on the screen. The enzyme that catalyzes the carboxylation of glutamate side chains is known as glutamate carboxylase. Okay? And vitamin K is a cofactor for that. You can see in the process that, of course, I've added a carboxyl on the gamma carboxyglutamate molecule on the right. It's shown in red. And now it can bind calcium, as I've shown you earlier. In the process of putting that carboxyl group on, vitamin K is converted into vitamin K epoxide. Okay? Why do we care about that? Well, we'll see why we care about that in the next slide, because vitamin K epoxide has to be converted back to vitamin K, because if it's not converted back to vitamin K, then you won't have enough vitamin K and you will bleed to death. Okay? So, how does that conversion occur? Well, there's that vitamin K epoxide. Vitamin K epoxide is converted back to vitamin K by this enzyme known as vitamin K epoxide reductase, and yes, I think you should know that. Okay? You see that the cyclic oxygen intermediate on the left is lost, and moving to the right, water is released in the process. Now, it's this place where the blood thinners come into play. Okay? This molecule called Warfarin, also called Coumadin, is an inhibitor of the vitamin K epoxide reductase. It's an inhibitor of that enzyme. If you give a little bit, you inhibit a little bit, and you lower a person's level of active vitamin K. So when we talk about thinning the blood, we're not really thinning it, we're just reducing its clotting capacity. People on blood thinners include people who have heart issues, like fibrillations, where they have irregular beats, or people who are prone to clotting. Somebody who's had a stroke would be put on blood thinner. Or somebody that was worried might have a stroke would be put on blood thinner. Okay? There are two ways of thinning the blood. One is through this molecule here, and this is the most common one that's done. It's done by prescription. I shouldn't say most common, but it's the one that's done by prescription. The other one is done with aspirin. Okay? And that's a different approach that's used with aspirin. Question, I was going to say, questions. Yes, where? Right here. Is this why dogs are given vitamin K if they eat rat poisoning? Yes. So rat poison is also known as warfarin. Yeah. So when you're on blood thinner, you're on rat poison. And you think, oh, I'm giving this to rats, and they're just going to go bleed all over my house, right? Ugh, it's just disgusting, right? Well, most commonly when you get too much blood thinner, what happens is you die of hemorrhage. So your brain, you bleed in the brain or something like that. So you're not going to have rats bleeding all over your house. Okay. But warfarin was originally discovered and marketed as a rat poison for that reason. But it has a very important use in terms of acting as a blood thinner. Other questions? I've been doing a lot of talking today. Yes?
Can you clarify on the thinning of the blood, you'll have hemorrhage in the brain? Isn't your blood vessels contain epithelial tissue?
Mm-hmm. So the question is, how do you get hemorrhaging if you have all this epithelial tissue that's there? What you don't realize is how often that clotting process is taking care of even the smallest of wounds. So if the smallest of wounds aren't being taken care of, which are happening by doing that, for example, then those wounds don't get fixed, you're going to start bleeding. And that's where the hemorrhaging actually occurs. So I'm not saying that you're not damaging the epithelial tissue, but I'm saying with hemorrhaging, even the smallest of wounds cause problems. And you're much more likely to have a small wound than you are a big gash and die from that. Okay. So vitamin K is also important. See, how am I doing on time? I'll tell you, you guys have been patient today. Why don't we go to the song? Today's song I cannot sing, but fortunately I have a recording of someone who does a magnificent job singing it. And so I hope you will try to join in with this metabolic melody. It's about the blood clotting process. It's to the tune of an old 1960s song called Don't Sleep in the Subway, Darling. And it goes like this. Okay, guys.